All right. Welcome everyone to this open lecture on AI and machine learning. I'm here with our guests from Calejo, Leonard and Johannes, who's going to do this presentation for us. This open lecture is also part of a course that we are given, and I'm going to talk more about that in the end of this lecture. But I would also like to remind you all that we have a Menti where you can log in, so you can ask questions even if you are on distance and online. So you just log in there and you enter this code, and then you can write your questions there. And then we will handle all of those in the end of the presentation. And I think that's all I'm going to say now, and I'm going to leave it over to you, Johannes.
Thank you very much. So, my name is Johannes Holmberg, and I'm representing Calejo, which is a company founded by me and my colleague Leonard, which is an AI expert and focused on machine learning, and also his daddy, the journalist Johard. Together with a network of a lot of skilled researchers within AI and mathematics and different topics, we have founded the company Calejo Industrial Intelligence. The company is focused on optimizing processes within the industry using AI. We have been using results from Leonard's research over the years and make a tool of that which is focused on optimizing industrial processes. We are very happy to be here at Mid-Sweden University today because the company, even though it's our team is spread out for the moment, we are founded and based in Sundsvall. I have, during the last 15 years, been working with industrial development in different ways. I have had the opportunity to work with very skilled persons within automation and robotics, also within lean management, and PLM and such different softwares and methods. And using AI is adding something else. That is actually something that is we haven't seen before. And that is not only me, there is a lot of reports and papers that is telling us the same, that using AI in industry will add more than twice the effects on productivity than all other technology leaps during the last 100 years. And putting that in perspective, that will say that it's twice the effect of the introduction of the steam engine and the assembly line, and also twice the effect of robotics and all the industrial IT as we know it. And that is why we based and founded Calejo, and that is also why we would like more people to be involved in AI and machine learning. And helping us with that today will be my colleague Leonard. He will tell you about intelligence. We talk about the way of problem solving using AI. Also different type of AI methods and neural networks. We're going to talk about the buzzword digital twins and ending up with a look into the future of AI. So with that said, over to you, Leonard.
Thank you. So the first, I don't see the presentation anymore. Yeah, thank you. Yeah, so the first question we have to answer if you study artificial intelligence is, what is intelligence? We can have, it used very vaguely in different contexts and not always according to the strict definition. For example, is a computer intelligent? Is a web browser intelligent? Can a robot be intelligent? Well, the answer depends. If you take the definition here, that's the most common one. We have two criteria, which is adaptivity and autonomy. If we start looking at autonomy, it's the ability to perform in complex environments without constant user control. So, for example, an autopilot in an airplane, it's autonomous. Many computer programs can be seen as autonomous, but they're not adaptive. So what does adaptive mean? It means your ability to improve the performance by learning from experience. So what we're seeing here is we have two time scales that we're looking at. In the short term, we have a kind of behavior performed by the system. It reacts to its environment, or it produces some output depending on the input. And that is the autonomous aspect of it. The adaptivity is something that happens over a larger time scale. So after being autonomous many, many times, it learns to adapt and improve its autonomous behavior. And that is what's really new with artificial intelligence. It's a new paradigm in computer science then, that we have this constant improvement automatically. And this is the common definition also. Artificial intelligence is, it differs from intelligence just by it being artificial. So it's a computer or a computer controller, actually any kind of machine or hardware that adapts and then performs tasks commonly associated with intelligent beings, which is kind of a circular definition. But if you define intelligence as above, then this definition does make sense. So often intelligence is divided in two types of intelligence, or in particular artificial intelligence. You have the narrow artificial intelligence, which is what most research focus on today, and it's what follows the definition of intelligence that we had on the previous slide. That means it's some kind of constant improvements to some system that performs a task on a short time scale. Another topic that's quite hotly debated today is the general artificial intelligence. That means we have a system that can do more or less anything that a human can do. Little bit more fluffy definition in itself. And if you look at it theoretically, no AI can be truly general. There is a famous theorem called the no free lunch theorem, which means that every intelligent that is good at something is bad at something else, which is kind of a pessimistic result. But that is not a problem in practice, because what is the essence here is that we're intelligence in this universe. And every general intelligence, for example, humans, have adapted to finding patterns that are common in our universe as a result of the basic physical laws, which is also a topic of research right now, quite hot, that previously system adapted and they learned, but nobody knew truly why. So now people are starting to look at the physics and trying to find these kind of patterns that explain why general AI is possible at all. So a common definitions then of general AI is the Turing test. So how to tell intelligence, a general intelligence and a weak intelligence apart is by, well, we need to give them some task and show that they're inseparable between humans and computer. We cannot tell them apart. And the Turing test is one famous test for artificial intelligence, where you basically give a human some kind of interaction. Usually it's a chat functionality with an artificial intelligence. And then you see if the human can tell whether it's an artificial intelligence or a human behind a computer. The little bit of a problem with this test is that it doesn't actually test artificial intelligence per se. What it tests is the behavior, not the ability to adapt. So this test was first passed in 1966 by Lisa chatbot, which sometimes managed to fool humans that it was a human itself. In 2014, for example, was the last time it's been tested and passed, when another chatbot fooled 30 judges in 5-minute chat conversations pretending to be a 13-year-old boy. I mean, it's these systems are not necessarily intelligent, but any well-written chatbot can pass this test as it's designed. So it's not a perfect test for intelligence. CAPTCHA is more interesting, actually. CAPTCHA means completely automated public Turing test set to tell computers and humans apart. This is also not correct because it doesn't separate computers from humans. What it actually tries to separate is intelligence and well, non-intelligent systems. As an example of this is that 2014, if I remember correctly, yes, Google defeated CAPTCHA in 99.8% accuracy, which means that computers can solve this problem. But cannot solve this problem is traditional computer programs. To identify objects is one of the challenges that traditional computer science failed to solve for a long time, using a lot of statistical methods and also handwritten computer programs. These kind of problems solved first with deep learning, when they started to apply a completely intelligent approach to this problem, basically training it on lots of images. And after that, it started to perform as well or better than humans in image recognition. So this test is indeed a much better test for intelligence than the Turing test. So the field of AI and machine learning, well, they sometimes used one equivalent to the other because there's it's a mixture of scientific fields. There's math involved in terms of solving these problems, adapting its optimization. We have biology involved because that's where modern systems take the inspiration from biological intelligence. And there's computer science in looking at the time scalability of algorithms and how to implement them efficiently on computers and so on. AI is the larger field, anything that studies intelligence in computer implemented or machine implemented systems. Machine learning has a bit of funny history. So machine learning was basically a result of a long AI winter when AI was mostly expert system, that is handwritten symbolic programs that didn't perform very well, but was very popular in trying to explain how computers could be equivalent to human intelligence during up until the 80s, basically. Machine learning then was a new field, but it decided that this doesn't work. We need to look at how biology does this and adapt to systems statistically and so on. So they created the term machine learning, which is more or less equivalent to artificial intelligence if you look at the meaning of the word, just to distance itself from the expert systems. And these expert systems didn't do very well historically, so it's more or less a dead field these days. So these days, if you say machine learning, it means artificial intelligence and vice versa in practice. The biggest field within machine learning is neural networks, and neural networks today are using the buzzword deep learning. They are also equivalent today, so we put just deep learning here. Neural networks is systems inspired by how the human brain learns, and deep learning is basically very big such systems. There's a bit more history to how this term was created, but was based on a lot of hypotheses which were proven not to be entirely correct. So in the end, deep learning just became regular neural networks, but bigger. So focusing on what is machine learning? Machine learning is a technology where models of reality are developed and trained on collected data. That is the most common issue we're having, that we need more data whenever we train models. If somehow an AI doesn't solve the problem, we collect even more data and more data and more data until the problem is solved. If you look at it historically, I mean, the first methods that can be, well, this is a very old way of thinking of things. I mean, it's basically intuition encoded into a computer. Even old methods such as the old farmer's almanac, when you use different kinds of predictions to predict the weather and the harvest, the common season, can be seen as a form of early machine learning with this definition. So what is really new with machine learning compared to statistics and well, encoded intuition? What's really new, if I can stay on the first slide a little bit. Yes, what's really new is the scalability of things. So it's a theorem also called the universal function approximation theorem, or neural networks are called universal function approximators, which means that it's a simple algorithm. You can just scale it by adding more neurons, and then you can solve any problem. And that is the new part of it, that if you don't have enough neurons, you just add more, and eventually you can solve any problem given enough data. Sorry, next slide. So a brief history on the development of AI the last 60 years is that the perceptron from 1958, there's also earlier work by Donald Hebb on Hebbian learning, when they looked at how neurons perform, doing measurements on neurons in different scenarios and see how the connections between them grew. And then they created a series of early models. Perceptron was the first one that learned meaningful, I think, and there was a few other ones that in those dates. And after that, unfortunately, the field entered what's known as the dark age of AI. There was a book, The Perceptron, by Minsky, for example, that had a big impact, that showed that these early models couldn't learn anything. They were actually quite limited because they were completely linear and the equivalent to a linear regression or something like this. And no matter how many neurons you poured on it, it would still be a linear system, not able to solve a simple XOR problem. And this lasted for several decades until the 80s, when this field got a little bit of funding by a few research groups, and they started making a lot of progress also with wider application in computer systems, and it's easier to program and so on. And the backpropagation algorithm and a few other algorithms that was developed in the late 80s, and this field saw a little bit of a revival. Reinforcement learning is a different field of AI that started growing in the 1990s. So a few years later, we have Q-learning, SARSA, policy gradients, and several other important algorithms appearing around the year 1990. And the latest development is essentially deep learning. It's not so much of a theoretical development. This is an improvement in computer system, improvement in problem solving, and that the computer started to solve real problems successfully that attract a lot of attention to the area. And this attention brought better systems, more funding, and so on. So it's really been booming since 2006. So if you look at problem solving with AI, it's a bit different approach than traditional solutions, traditional methods. For example, if you have a problem, you want to control a factory or something, then you write a computer programs and you guess a little bit. You try to figure out how to make a good control system until, I mean, it's quite an unstructured way to solve the problem. AI methods are different because the problem solving is automatic by the adaptive systems. So the focus here is not on how to solve the problem. The focus is on how to structure the problem. You need to formulate the problem very precisely. Then you press enter, you go take a coffee, you come back 15 minutes, maybe one day later, and you look at what has happened. If it doesn't solve your problem, then you have a problem with the problem. And you try to formulate the problem again, press enter, and take a look if you describe the problem more accurately this time. Most important is the computer will cheat whenever it can. So if you give it a shortcut in how to do things, it will find it and it will exploit it, and you're not solving the real problem. In particular, a famous quote is, if you torture the data long enough, it will confess to anything. And any adaptive AI is a professional interrogator. It will interrogate your data and give you the result you want, or the result it wants, as you formulated the problem. In particular, a specific example of this is the Texas sharpshooter fallacy, when you have it's based on an old joke. You take a gun, you shoot at the wall, then you move, you paint some circles around your bullet holes and say you're a sharpshooter. And this is a scientific fallacy that's underlying it, and the AI will do this every time if you let it. Looking at the problems that AI can solve, we have 3 simple examples. It's chess, it's backgammon, it's poker. And the question arises here, which of these problems is AI actually good at solving? Well, we can look at the other way. What is humans good at solving using traditional methods? If you want to write a computer program, well, you have chess. It's quite deterministic. You can't have any random chance at all in it. It's just completely logical. But if you look at backgammon, there are dice involved. It's a bit stochastic, so there are many possibilities that you need to model. If you make one choice, it can actually lead to several different results. And then you can look at poker, which is even more random, and also about predicting a lot of hidden states about what the other players are thinking and their behavior, other players' cards that you know of, and so on. So it's much more complex in terms of modeling the actual state of the game. And this is matched also by the computers, how long it took computers to solve these problems. If you look at chess, already in 1976, it was beating expert players and winning tournaments. It didn't need any AI to do that at all. You just write a traditional program to do it. While backgammon was a game that actually required AI to beat humans. And it was TD Gammon, written in 1992, and between 1992 and 1995, it made several improvements, and it was equivalent to master players by 95, if not before. And of these, poker, maybe not considered the most intellectual game of these, but it's actually the most difficult to solve for a non-intelligent system. And it was beating expert players only in 2016 in tournaments. So, as we said before, we focus on problems when we do machine learning. The actual methods is not as important as the problem definitions. So if you look at different AI methods, we start with looking at different problems that we're solving. The first one is supervised learning. It's quite simple. You have an input and output, and you have some system, for example, a human that sees an image and outputs what is seen on this image. Is it a cat? Is it a dog? It decides. And if you want a human to learn this, you just have lots of classifications for a human. You show it to the computer. Here's a cat, here's a dog, and so on. And you do this a few million times. And each time, the computer calculates the difference between the human's decision, its own decisions, and it tries to adapt to reduce this difference. So in the end, it gives the same classification as a human, practically. And all systems are continuous. So what you usually get as an output is a value between, for example, 0 and 1. And to do classification, you take and convert this 0 to 1 value to an integer. So it can be cut at 0.5. So everything below 0.5 probability is a dog. Everything above 0.5 is a cat. And this makes it all classifications into a regression problem. Reinforcement learning is the other big, well-defined problem that AI can solve. We have a much more limited feedback here. It's known as a reward. So instead of being told what is right output, for example, how to move, what to say about this animal, what it is, and so on, all you get is a reward, which can be a number, any kind of number. And over time, you want to get as much of this number as possible. So it's basically like giving, candy to a dog or something, and the dog wants to get as much candy as possible, and it tries to figure out a behavior that achieves this goal. So you have an observation A that you show the dog, for example, you give it an instruction, then it does something, and based on some result of this action, it will get this candy. So over time, it will learn to obey you, hopefully, unless it's not a dog. Next slide. Unsupervised learning is the third problem. So these three problems are usually all machine learning systems can be classified in one of these problem types. And that is basically due to unsupervised learning not being properly defined. Unsupervised learning is kind of a garbage bin where you throw all problems that do not fit in the other two categories. And still it's quite rare. So the other two categories are the most common ones. But here you have different kinds of classification systems, automatic grouping, and there are also automatic map creation using data and so on. For example, here a very simple example of different kind of observations of different colors, and you group similar colors into the same groups basically. It's a type of unsupervised learning. Unsupervised learning is also used in a lot of recommendation systems online, like Netflix or Spotify use these kind of methods in order to recommend content to users. For example, if you've read one article, it can find a similar article for you by looking through a lot of creating some similarity measure between articles. And also you can find similar users depending on what you're reading, and then you put you in a group and you recommend new content depending on what you've seen previously. And as I said, there are many machine learning methods. If you look at the actual algorithms and not the problem formulation, too many to mention. This classification is not perfect, but there are really tons of methods. What is interesting about it is that if you look at it in a deep theoretical level, all of them can be transformed into an equivalent neural networks. So more than 90% of all methods are neural networks in disguise. So looking at just the neural network method, you will understand most of them, and you see that they are kind of a simplified version of neural networks. And that's what we're going to talk about next, neural networks. Neural networks is, as I said, the most common methods these days and the most promising one. It was originally inspired by human brain by looking at neurons. We did electrical measures on the transmission of neurons and how the transmission changed over time in both in live animals and in the isolated neurons in petri dishes and so on. So if you look at the human neuron to the right, we have a lot of dendrites, which is the kind of the trees growing from the cell, and these are the input. Then you have the nucleus, where you get the signal, and it's transformed a bit, not completely linearly, in order to make a threshold, and once it reaches this threshold, it sends a signal to the axon. And modeling this in a simplified way is on the left, where you have an input X, you have a sum, it sums all the signals from the dendrites, and then you have activation function, which is the nonlinearity in the cell body, and your output, which is the signal that goes in the axons. They're mapped almost perfectly one to the other. These simple neurons are then stacked in what is known as neural networks, and most systems use a layered approach where you have an input layer, you have one or more hidden layers, and you have an output layer. So input layer, there you basically put your data, force it into the neurons. In the hidden layers, it does its calculations. And output layer, you just take the value and you output it to, for example, a control system, or send it to your classification or anything like this. So all the calculations happen in the hidden layers. And this is a modern system, GoogleNet, a few years old already, but as an example of how modern neural networks look, quite complex, 6.8 million parameters that optimize at the same time. Each block here is one layer with thousands of neurons. So, and then you stack them on top of each other, and then you have some different kinds of layers you combine in different ways in some patterns, and then you get a result. It's quite experimental science. They just try different layered structures, see what works best. And they do this many times, not always in a structured fashion. People just try whatever works, and then they get a good result, publish it, and then other people start experimenting, starting from their architecture. So if you look at what discussed earlier, then neural networks is automated automated statistics, and in another perspective, it's automated science. And science is modeling the real world. A model is a twin of the real world. So every artificial intelligence is in a way a digital twin. So digital twin is a buzzword that's been used a lot, especially last years in industry, when industries realize that they have to create models of their industrial processes in order to understand them better and for them to be optimized using computers, and there are many other different purposes of digital twins. It's not necessarily a new concept, since digital twins, all industries had some model of the process, but it's very unstructured, and now this has been a focus to improve the modeling of industrial process in particular, but basically any physical system is the same problem formulation. What we specialize in is Graybox modeling. If you start with a simple model here, we have a real process, a coffee maker, and then we want to create a model of it. And typically people use something called reductionism, that is they divide the process into simpler components that's easy to understand and try to model these. And if these are too complex, you can divide it into even more components that are hopefully simpler and so on, etc., etc. And you get down to some systems are simple enough to model using physical models. That's the theory. In practice, it doesn't always work like this. Because it's difficult to use for complex processes. On the left, if we want to model the water flow, we have, it's quite simple. You have the volume is equals to simple algorithm for the volume. We know how it works. We can calculate flows from there. The water flows out, the water flows in. It's easy to model. On the other hand, if we want to model how the filter works, we are in a bit more trouble. And there are actually several PhD theses working with this. How to model the chemical process inside the filter and how it influences the coffee quality. And if you show this is how they look like, and this is just a little excerpt. There are much more of those. It's extremely complex, and when things get complex, people start failing at modeling things because it's too difficult to do properly. There's so many unknown constants you need to model, and even if you have these constants, the model might not be perfect. Additionally, it takes a lot of time. As I said, there's 30 scientist years or more of science put into coffee filter modeling only, and still they didn't succeed in coming up with a very good model. On the other hand, if you use an adaptive intelligence, then it's quite simple. You just collect data, input, output. If you have the data, this modeling can be done in 5 minutes. Just structure the problem. I want to model the output based on the input. You collect the data, you press enter, you take your coffee from the coffee brewer, come back to your computer, and it explains how this coffee came to be. So what is the advantage of physical models compared to black models? The physical models can be much better understood and analyzed by humans. So if you have a volume, you see that it's overflowing, you think, maybe I don't have enough volume, I just increase the height a little bit. It's very intuitive. On the other hand, communicating, interacting with a black box AI model is almost impossible. What does it mean? There are 6.8 million parameters, for example. Which of them influences the coffee quality? How should I change the model in order to model a bigger container, for example? Well, you have no idea. You just need to collect more data. And real processes like industries are constantly in change. So the industry that was this year had some machines changed, had some renovations, maybe some expansion of some capacities and so on. So all the data you collected is worthless as soon as they made one change. So data is not reusable at all, and you always have to collect more data, and you never really reach the state when you understand the process. This doesn't happen with white box modeling because you understand what goes on. So with Graybox modeling, you combine physical models with AI models, and you come up with the Graybox model, which hopefully combines the best elements of both methods. Where you have a limited process you don't understand, you put a black box there. With the white box modeling, you can model physical systems that we can create models you can reuse and so on. And it becomes very nice together in a practical sense. This is not just something we use in industrial modeling. This is also the trend both in physics, we use more AI modeling, and also in AI, we start to understand that physical modeling is important in order to have reusable models. So understandable AI models is a big topic right now. As an example of the benefits, you can see here we have a typical industry. We have two different parts, and let's say we see if we input something in place A, how does it influence the output at place B? Well, if we want to do this with a white box traditional model, that means a physical modeling, we need to create a physical model of every component in between, the containers, all the machinery, the pipes need to be modeled precisely to calculate the fuel flows and so on. And this becomes a very heavy task. You can spend easily months or years in just trying to model this using physical tools. While on the other hand, with a black box, you can just set up the problem, collect data from A, collect data from B, and everything in between can be approximated by this model. You don't need to know what's in between. You don't need to model it. You don't need to understand it. You just collect the data, which saves you a lot of time in these situations. Not as reusable, but the gain in both performance and time spent more than compensates for that in most cases. So in general, artificial intelligence is about pattern recognition. So we're trying to predict how the future looks like, and the physical systems can be seen kind of like an orchestra. So if you listen, if you have one instrument, the violin 2 here in this case, and you don't know what to play, you can just start listening to the rest of the orchestra, and you can figure out, if you have trained a long time on this piece, how to play to what the other are playing. Say you want to improvise, for example, you can also start filling in the tones in a meaningful way, depending on all the other music that you hear. So in this case also, you could have somebody leading the orchestra, so playing certain instruments and then making everybody else follow the instruments. And this way you can control any physical systems. You just decide that these two set the pace for the rest of the orchestra, everybody else follow them, and then you create a musical piece that can be controlled by two instruments. Or in terms of factory, then you have the whole physical models can be controlled based on, for example, your input wood quality, or depending on your desired energy consumption and so on. So it becomes very flexible. Most physical systems are redundant information. You can focus on just some aspects of it that can then be used to predict how the whole other process will function, even if it's very complex. So you don't need to know every state of every part to make a good prediction of how the events in the plant or in the musical piece will unfold. These systems we have been using in a number of practical applications, including hydropower, wastewater systems. We have used it in mining and pulp and paper plants. And all of them are facing actually a very similar problem, that they have a poor understanding of the current systems, and they would like to improve them somehow. And if they only had a better understanding, they would know how to optimize them. But there's essentially very primitive methods used in the industry today to model things, linear correlations. They need to stop the process to collect data and so on. But with AI, you can really create a new generation of physical models. And this will have a very big impacts both on energy efficiency, energy production, and environmental concerns will be improved by reducing fuel consumption and so on and so on. So we can see the impact on the industry right now. And most industries have a plan for how to start using AI systems, well, everywhere. Although it's not always an easy way for them to go there. So I would like to conclude with a little bit of insight into the future of AI. Very superficial, so to say. I just can't go into too much detail, so I guess in this short period. But what's hot right now, especially in terms of industry, is predictive maintenance to anomaly detections. You basically analyze the plant. It can be considered a type of unsupervised learning. You just look at all the measurements you come in from the various sensors in a factory, and then you try to detect that when something is not ordinary, something strange that needs to be analyzed further. And usually this is in order to predict when there's some maintenance need. For example, when a wheel is about to break, or something has happened to some pipe, or something that needs to be analyzed further. We also see a lot of AI technology added to traditional control and modeling systems. As I mentioned before, most of them have some model, and then they try in a very limited fashion to add some little AI blocks to their models, so trained with their neural networks in a special research project or something like this. And then also there's a lot of effort into streamlining administrative processes with the help of AI. AI has been used a lot in, it's easy to work on giving advice to humans. To actually create autonomous control is a big step for many industries today, but giving recommendations or assisting with more soft factors, such as inside the system without actually controlling anything, is a big topic. And this is similar to the automation stages of autonomous cars, for example. Now it's more about giving recommendations, but we see that industries have already started looking at creating autonomous factories, but that's still some years off. In the coming years, we see other developments happening. The user reinforcement learning is growing quickly with a lot of applications, especially optimization. There's been some well-published successes for reinforcement learning control, both in control of energy systems, but also with DeepMind, when they play computer games and so on. So some seems promising enough for them to start being introduced everywhere. So companies that run optimization programs for industry are having research projects in place right now where they're doing reinforcement learning as optimization tool for all these processes. Also, AI-based support for operators, a little bit mentioned before, but this will continue to grow. That AI will help the operators in industries to take the right decisions. A bit wider in AI is the automatic differentiation. Automatic differentiation is interesting because it's a system that takes a traditional computer program and makes it adaptive. So by running a computer program code through an automatic differentiation engine, suddenly the whole computer code can be improved by small changes and start adapting to some data. So we're starting to see more of this, that people have converted anything from simulation engines to graphics engines and mapping systems and anything you can imagine with this automatic differentiation to start improving the computer codes, regular handwritten computer codes, using the same machine learning methodology. And yeah, we also see AI starting to be introduced in traditional software a lot. For example, in small compartments, they do some tasks better than traditional system, especially image recognition these days, but also like in rendering, creating images, and all kind of creative tasks or intuitive tasks are being taken over by AI quickly right now. So this is what we're seeing currently. I mean, in terms of the industry, that previous technology support with most digitalization and some automation has finished by now. Most systems today are, or most industries today are digitalized. And now people are looking at the AI-supported industry, which is an even bigger challenge for them and even bigger potential. It's starting to take off now to make small steps. It hasn't really created, they haven't really created any AI-supported industries yet, but everybody's working on it. And all research indicate that this will be a giant leap in both the performance and the automation level of industries. Yes, as the company, we are in the forefront here in developing the tools based on a lot of mathematical and also practical knowledge for how it runs in order to create the best toolset for this. And about a machine learning course, I'll let you take that. So thank you for your time. And yeah, I'm still here for questions later, or right now if you want.
All right, thank you, Leonard. We had to be on distance because of Corona, yeah. Of course. So I'm just going to talk a little bit here about the course. I know that some of you who are here listening online is, of course, already enrolled to this course. But basically, this has also been the first lecture in our in a course on applied machine learning. And this course is still open for enrollment. So if you have seen this lecture now and want to learn more, you can go in and you can actually apply to get enrolled on this course. This course is part of our initiative to give courses to working professionals. So it's a very flexible course. It's fully on distance, and it's made to be combined with our already working at the same time. And because you can enroll right now, so the next lecture we will have in the course will also be in 2 weeks. So there's some time for you to enroll and get registered and all of that. So the next lecture is in 2 weeks. The course in general is 10 weeks long. It gives 3 HP. It's on advanced level, and it's, of course, since it's a university course, it's free of charge. And as I said, it's made for working professionals. It's quite slow speed. You can work in your own time. And it's in the end, we also have the opportunity to do a win-win project. So you can do some let's say you're working at a company, you can do some project that actually would benefit you in your working at your company. To apply, you can of course find it on antagning.se, where you find all university courses, but easiest is probably to find it on our website. So you go to mion.se/iprof, and iProf is our initiative for these IoT courses for professionals, basically. And there you can find the link to apply for the course. The only requirement to be enrolled on the course is that you need to have a degree, a bachelor's degree, kandidatexamen, in computer engineering, computer science, electrical engineering, or something similar. And you also need to have some programming courses with you in this. So with that, feel free to enroll, and we will start the course as soon as possible here. And you can also, the course starts today, but the next lecture is in 2 weeks, but there are already some elaborations and stuff up on the course. All right, I think we can actually go back to the Menti page. So we do like this. So if someone has, so if someone has more questions, they can also log in now and add their questions. So I will ask you then some questions, and maybe Leonard on distance can add if he wants to. So what is the advantage of reinforcements compared to logistic regression? Maybe this is more of a Leonard question.
I think so, yeah.
Reinforcement learning compared to logistic regression. Yes, so logistic regression is a type of supervised learning. So there are different problems. Supervised learning, it requires you to know what the desired action that the network should do is. For example, if you have a robot, you need to tell it, I want you to move to the right, but you move to the left. So you did a mistake. With reinforcement learning, you have much less feedback needed for the robot. So for example, it moved to the right, but you didn't know where it wanted to go. You just wanted to take a ball and throw it or play baseball with it or something. You only need to, for example, give it a reward then when it scores a goal. So while in supervised learning, you would actually need to figure out how to move and how to perform every action in order to score that goal. So reinforcement learning requires much less feedback, and in many problems, in many real problems, you don't know what the ideal behavior is, and then reinforcement learning is much more appropriate.
Right. Thanks, Leonard. I think the next question is perhaps more towards your area. So how do we, as people, assure that AI and machine learning are applied to user interfaces, but also the ethical and solidarity aspects of it?
I think that is a really good question, because and something that we actually are focusing on, and that goes back to the slides we showed about the Texas fallacy, the sharpshooter fallacy, for example. It's really easy to show and find solutions to problem that you actually don't know the the problem, so to say. You need, as Leonard mentioned, you really need to figure out what type of problem you need to solve, because there's always a solution. And that goes back to the ethical parts of it as well, that you actually need to know that you are handling the problem in the right way. And of course, there's a lot of other issues regarding this. If you, for example, talk about personal data and things like that, you really need to know how to handle it. Otherwise, there might be problems. Yes. We are focusing on the industrial problems, and so in our point of view, we are not often issues with personal data in that way. But that is something we actually need to handle, of course. Really important things to do.
It's a problem. It's very much discussed in the AI and machine learning areas. And then I sort of have a question from my perspective. Let's say all these prospective students that are taking this course then, what do you think they should sort of focus on in this course? What is sort of the important parts to take with them?
I would say, apart from the programming part, which is of course what you're actually going to learn in the course, but I think the focus on what type of potential AI will give that area that you actually work in, so that you realize what type of problems that you can solve with AI, what AI is compared to other tools and solutions and methods. I think that, so we actually start to discuss that, what type of problems we can solve and the potential using it. Because even though the course is 10 weeks, you will probably only scratch on the surface on it. So in order to dig in deeper, I think it is a good thing to keep in mind. What type of potential am I looking for, and how do I find it?
We have some more questions here. We can continue with some more. So how can we decide the quality of the AI model if we put two different models sort of competing against each other?
Well, there are several ways to do that. And I think Leonard is much better to if we address that question to Leonard instead.
Sure. Can you repeat the question, please?
So how can we decide the quality of AI models if we put two different models sort of competing against each other?
I can't hear from here.
Oh, sorry.
No.
How can we decide the quality of the AI model if we put two different models competing against each other?
Well, there's a the simplest method, and the one widely used, is to have a separate validation set. So you take your data, you split it, you use one part of the data for training the models, and you train both models on the same data. And then you keep the validation set secret. So once the models have been trained, you show them this remaining data, and you see which one performs best on this unseen data.
Let's see what other questions we have here. Well, I think we can take this one also. Maybe that's a Leonard question.
Yeah, read it, please.
Okay. What are the computational costs associated to different AI implementations? Sort of like statistical, supervised learning, unsupervised learning, so on.
Computational costs of different models, or?
Yes.
Into the last part, yes. I mean, almost all AI models that are used today scale with a number of parameters. You have twice as many parameters, it takes twice as long time. And that's true for supervised learning, at least. Reinforcement learning has a more difficult development of the learning costs. So there is not yet at the efficiency of supervised learning, but using some new methods and simplifications, it can approximate it. What this means in real hardware is today you train, of course, all AI systems. Well, you can do some simple things, usually in industrial problems, quite simple on your computer. But for image recognition and like the Google Net, where you have much more parameters, you train them on GPUs and possibly also in the cloud, divided on several GPUs.
And Leonard, if we compare that with traditional way to build models in regarding costs, and implementation time. Can you comment on that?
Yes, so traditional models. Well, the training is in terms of the cost for the computing, it's nothing. You know, you can spend maybe a few hundred crowns or something like this on training costs, up to a few thousand. But on the more complex system, on a very simple system, it's 15 minutes of your computer, whatever you value that at. In terms of development time, well, as you can see, for example, for the coffee filter, if we do a model for that with physical model, it was at least a few years of research time, while an AI system can do it in, I think, 15 minutes. Plus, if you want to code the system, maybe half an hour or up to half a day, depending on how much data formatting it is. But it's a completely different time scale in terms of consumption of human resources. So.
And also, of course, a question of the quality of the data, of course. So it's
I mean, when you train AI models, generally, it's the data cleaning, collection of data is the biggest part. I think just writing the code is 10% of the total time, or 10 to 20% has been estimated that is the actual programming, and with 80% is just like project management, collecting data, cleaning data, figuring out why it doesn't work by looking at the real process and so on.
Okay, I also got two questions here regarding the course itself, so I'm going to answer those. Okay. So one question is, why do you need 15 HP programming in a bachelor degree to enroll in the course? I mean, there's many people that are doing it without any technical degree. And the reason for that is both a technicality in who is financing all these courses. The course is on advanced level, meaning that it's sort of meant to be on sort of the 4th, 5th year, or sort of like a master's level on it. So that's why we have this this requirement here. And also 15 HP programming is just that we do a lot of programming in this course. It's a computer engineering course in AI. It's not a statistics, not a mathematical course in AI. It's a computer engineering course in AI. So there will be Python, TensorFlow elaborations here. And that's just for you to be prepared. You need to have some programming expertise on this. Otherwise, it's going to be super complex for you to do. So that's why we have the 15 HP and the degree as an enrollment requirement. And then I had some other question that someone that actually enrolled and got put on reserve. I have to look into that. We're planning on a sort of letting everybody that fulfills the requirements is going to get let in. That's the plan. So I will make sure that you, if you get placed on reserve, we will let you in as soon as possible, basically. But that's the idea. If we reach over, I don't know, 100, 150 students, maybe we will start stopping students. But basically, we will let everybody in that wants to get in on the course and fills the requirements. All right, I think that's the questions that we have. And with that, I want to thank you for coming and doing this.
Thank you for letting us.
Yeah, thank you.
And I want to thank everybody that's listening from home and participating. And hopefully you will think about enrolling to this course. And then for all the students, we will see each other on the next lecture, basically. All right. Thank you very much.